Today is Sunday, April 18th, 2021. Today, we're going to discuss the cosmic microwave background radiation that was discovered in 1965. After 25 years of research, astronomers Arno, Penzias, and Robert Wilson discovered the microwave background radiation, the cosmic microwave background radiation. Now, Einstein and his cohorts 40, 50 years earlier didn't have the benefit of the cosmic microwave background radiation. Now, what's significant about the CMBR? What's significant about the cosmic microwave background radiation is that it tells us that the universe is isotropic, the same in all directions. Anywhere you go, it's going to be at 2.725 Kelvin. That matches a certain frequency of electromagnetic waves. So immediately we know that the universe is finite. You say, Adoni, how do we know that the universe is finite in volume? Well, in order for electromagnetic waves to homogenize to one frequency plus or minus 4,000th of that frequency, actually it's to 10,000th, the 4/10,000ths or 4,000ths. Anyway, to homogenize to such a level in all directions, the electromagnetic waves must bounce back from the edges of the universe. And we know from the Hubble flow redshift, that is an excellent barometer for measuring distance in the universe. We know that the universe has a diameter of at least 22 billion light years. Okay? So that's definite. The diameter of the universe, according to the Hubble flow measuring stick redshift, has a diameter of at least 22 billion light years. Okay? So now the light must bounce off from the edges of the universe an infinite amount of times in order to homogenize to one microwave radiation. You can't do it just from one bounce back. It has to bounce there and bounce back and bounce there and bounce back and bounce there and bounce back. And then you get a certain bounce. Okay, we define God particle 1s as the smallest particle of mass. Okay, GP1s are the smallest particle of mass. And what the cosmic microwave background radiation measures is the frequency of the bounce between the God particles. Okay? Not so much the bounce, because the bounce is at light speed, but it's the peak and ebb of the bounce. So what happens in microwave radiation is that there is a peak, an amplitude, okay? There's a peak compression. So you have the highest compression of the wave, and this happens gigahertz. We're talking gigahertz here, okay? Many times a second, okay? So the GP1s can bounce back and forth many times a second, okay? And then there's a peak compression, okay? When they get pushed together the most, and then they push apart. Most apart. And this has a certain frequency. I think it's 1.6 gigahertz, something like that, is the cosmic microwave background radiation. I forgot to write it down. Okay, so since it's the same in all directions, and since the light, the waves, the GP1 waves that make up this radiation, okay, so we have all the way from gamma waves to radio waves, okay? They all go to the edges of the universe, okay? Now, if there were no edges, they would just keep going, and there would be no microwave background radiation. So the first reason we know that the universe is finite in volume is we have the CMBR. And because we have the CMBR, we know that waves generated within our universe do not propagate forever. Okay? If they propagated forever, there would be no microwave background radiation. So because of the discovery of the microwave background radiation, we can update the theories of the 1920s and 1930s, prove conclusively that the universe is finite in volume. And it has a diameter of about 22 billion light years. And also that the universe is infinite in age. Okay? Now, there are many ways we know that the universe is infinite in age. Okay, and in this case, we know that since light waves, in order to homogenize and create an isotropic universe, they have to bounce off the edges of the universe an infinite amount of times. Okay, so it's an infinite amount of times, and each time they bounce off is 22 billion years, okay? So you multiply 22 billion years by an infinite number, and you get a very long time, okay? Now, there are other ways that we know that the universe is infinite in age, okay? We can take the life of the proton, okay? The proton has a half-life, we're given a half-life of the proton of at least 1 with 35 zeros after it, years, okay? That's a very long time, okay? So no one can say that the protons we have today weren't made a quadrillion times a quadrillion times a quadrillion times a quadrillion years ago, or 1 with a quadrillion zeros years ago, okay? So if you can't pinpoint the age of the proton, how can you pinpoint the age of the universe, okay? Now, the lifespan of a stellar black hole, okay, that's the time it's going to... Well, first, let's discuss what a stellar black hole is, okay? If you have less than 2.16 solar masses of neutronium or less, you have a neutron star. And we know that a neutron star, the density of a neutron star is 80 billion times the density of the Earth. Okay, so, and the only way that you can compress 80 billion Earths into the size of our Earth is through a process of compression, decompression, compression, heat exchanger, decompression. And you get the neutronium down to 240 billion negative Kelvin. Okay, neutronium is very cold. Now we know this, excuse me, we know that neutronium is very cold because it sucks the GP1s, the God particle ones, it sucks the warmth out of the cosmic microwave background radiation, okay? It sucks it so fast, okay? It sucks it so fast that the medium in which electromagnetic waves travel in, the medium warps, okay? So we can see the backside of a neutron star. Okay, now once you get above 2.17 solar masses of neutronium, the neutronium develops an event horizon. Okay, so that's what they call a black hole. It's an event horizon. Now, the event horizon for a stellar black hole is not that far from the neutronium. Now, the supermassive black holes, the event horizon is much farther from the neutronium, so you don't have such strong tidal waves. Supermassive black holes do not spaghettify stars as much as stellar black holes do, because the distance to the neutronium is not that far. In any event, the life of a stellar black hole is given as 1 to, with 64 zeros after it, years, okay? The life to evaporate. Now, what I say happens with a stellar black hole or a neutron star is that it warms up. The neutron star warms up from minus 240 billion Kelvin. And as part of that warming up, it takes GP1s that make up the structure of space, it takes them from space, and then other GP1s rush in. But a black hole sucks the GP1s in so quickly, warms up so quickly, takes the heat from space so quickly that I turned the air conditioner on because I was hot. I am hot, I'm sweating, but it's making me cough. So I got a problem, but I'm making a good video. I hope you're able to follow it, okay? Because you will learn so much about neutron stars and white dwarfs if you realize that the only way you can make those compact objects is by the Siemens refrigeration process. Just like we make dry ice, okay? Stars compress matter. Now we know that the nucleus of an atom is like a pea to a racetrack. There's plenty of empty space there, okay? Plenty of empty space between the nucleuses of atoms. It's not empty. Plenty of space, plenty of structured space made up of God particle ones, the medium of electromagnetic waves. So every nucleus is separated, okay? Now, when you reduce the volume of hydrogen or nitrogen or oxygen, okay, you do it through the Siemens refrigeration process. You compress the atoms closer together. You take out the heat through a heat exchanger, and then you decompress and they cool. Okay, you compress them again, the heat, you remove BTUs from the heated gases, and you compress, and then you decompress them, and the gas cools, and you continue that. And then you can make liquid hydrogen or liquid CO2 that way. And then if you decompress the liquid CO2, you get dry ice, solid CO2. Now, stars do the same thing, okay? Through the process of compression, heat exchanger, decompression, cooling, compression, our sun is going to make a white dwarf, and it's going to become visible. It's making it right now, but it's going to become visible in about 5 billion years after the sun blows off half its mass as a red giant. There's going to be this remnant left. But this remnant doesn't just form in 5 billion years. It's already forming. And part of the heat, the radiant heat that the sun is putting out, is coming from the compression of matter into the white dwarf. Okay, you compress, you take out heat, then you decompress, and the matter cools. Okay, and it's the same thing with our Earth, where they found an inner core. Okay, that inner core is colder and denser than the outer core and the solid iron core. So you have a solid iron core, then you, underneath the solid iron core, you have a colder, denser inner core. Okay? It's the same thing with the sun. You know, you just keep going down, and you end up with a white dwarf at the center of our sun. Now, a white dwarf is going to be the size of Earth. So white dwarfs is the size of a planet. Now, neutron stars are the size of a small city, about 14 miles across, 20 kilometers, okay? So now there's a difference between the event horizon and the size of the neutronium ball inside a black hole, okay? So a black hole just has more neutronium, okay? And if you can build up the amount of neutronium that a black hole has to a billion solar masses or to 100 billion solar masses, okay? It can just keep adding more and more neutronium. Now, what they don't tell you is, okay, so the neutronium is at twice or more the size of a nucleus. I think it's given us twice. I didn't write everything down. I made some notes, but I didn't make complete notes. In any event, neutronium, even before you get to the neutronium inside a black hole, the neutronium that makes up a neutron star, that neutronium is denser than the nucleuses of atoms, okay? So another thing that you're not told is that nucleons hover, okay? They hover in the nucleus, they don't touch, okay? Nucleons are sacs or permeable sacs, and you have to get them very cold to be in the nucleus or to be neutronium in a neutron star or neutronium inside a black hole. Okay, we estimate that neutronium at 80 billion Earth densities is at minus 240 billion Kelvin. Okay. So when a black hole, okay, so gravity, we believe that gravity can only be generated when matter heats up. When matter absorbs, when nucleons absorb God particle 1s, and matter heats up, then you generate gravity. if nucleons net expel God particle ones from cooling, then you generate anti-gravity. Okay, so the voids, the dipole repeller voids, and the overdensities are the natural consequence of matter heating up for the overdensities and matter cooling, net cooling for the dipole repeller and stuff. So I'm starting to cool my voice. Next time we'll pick up on how you can think of voids as high ether pressure systems, just like we have fair skies and high air pressure on Earth, and the overdensities as low ether pressure systems, galaxies as storms, okay, and where the precipitation is stars. So galaxies are low ether pressure systems. They're storms, and voids are high ether pressure systems of fair skies. Talk more, different time. Bye. Talk more, different time. Bye.